So today we are going to do this 4.4, which is absolute maxima minima. But before that, if you want, I can uh, recall relative maxima minima first. Remember, in absolute extrema, you can say, or maxima minima, right? So what is absolute? Before that, in 4.2, we had relative maxima minima. So what is the difference between that? As I told you, relative is basically close to a point. These are all relative maxima minima, right? So these are three relative maximas and these are relative minimas. So uh, these three from here and these two from here. So these are relative maxima and these are relative minima. So the difference between these two is actually if you have something like that, let's say it just goes down from here, you see all three top points are relative maxima, but only one is the highest in the whole interval. So if I have this point C, let's say, right, then we had a condition that f of C is the highest value, f of C is greater than f of x, if I keep myself near to this point C. Means if I do not go very far, if I just take this piece of the function, just this piece only, then this is the highest value, right? You see, all other values are below it. Similarly at this point, similarly at this point. When x near C, so this is a relative maxima when x is close to C. This is the condition. But if I change this now to all values of x, for example, if my C is here now, right? If let's say this is my number C, and in this case, I can say that FC is greater than x is any point here. If I take any point x, x here, x here, x here, any point x, right? X is a variable. C is a fixed point. So if I say that if I take any x for all x in your domain or in your interval. So see, relative maxima, we say that x is close to C, x is near C. We do not go very far, right? So then all these 3 points, these top 3 points become relative maxima, but only one is absolute maxima. So this is the absolute maximum value. Reason is this, in the whole function, that is the highest value, not close to some point, right? So here I don't have to say that I need to keep myself closer to this number C, right? I don't have to keep myself this closer to C. If I say just close to C, if this thing is happening, then we say relative maxima. But if it is true for all x, then it becomes absolute maximum. Means this is the maximum value of the whole function, not just a small piece of it. Okay, so absolute is like global. As I gave you the example last time that Buremi region has its own head, the governor of Buremi, right? So her region will have its own head, right? So they are the maximum powers here. But if you talk about the whole country, then governor of Buremi is not the absolute power. Absolute power is the king or sultan of the country, right? So you may have in your own localities, you may have your highest level. But if I consider the whole thing, you may not be the highest. So this was the relative maxima, but it is not absolute maxima. This is also the relative maxima, but not the absolute maxima. Only this point becomes the absolute maximum. Okay? Which point? it's a point where function has the maximum value, right? So similarly, if we say that we have a minimum, so if this is true, if my fx is greater than or equal to fx for all x in the interval, then f has an absolute maximum because it is for all x, absolute maximum at x is equal to c. So similarly, if I say that function has a smaller value, see fd is less than or equal to fx for all x again. So it means no matter how many terms you are having, right? So if this is happening, you see, let's say this is the number d now. If this is your d, right? So see, the value of the function is the smallest. If you compare the whole function, all the function is above this point, right? So this becomes the absolute minimum. This becomes the absolute minimum, right? All these values are relative minimums. This one is relative minimum. This one is relative minimum, right? They are relative minimum values. This is also relative minimum value, but one of them has become absolute minimum, just one. So relative maximum minimum can be more than one, but absolute maximum minimum will be only one. So then f has absolute minimum. As I said, the president or the king or the sultan of a country is only one, right? But every governorate can have its own president, which is called a governor of that governorate. Governor of Brahmi, governor of Sharqiya, governor of whatever, right? Provinces or governorates. So they are the highest power. If you just talk about Brahmi, governor of Brahmi will be the highest power. Whatever he will say, people will accept, right? But as long as the country is concerned, people will not listen to him. They will listen to the highest power, who is the king. So absolute maximum is the king, right? Relative maximum are these small people. So there are many ways to find maximum minimum. For example, here you see in this type of function, there is an absolute minimum. You can see that here. This one is absolute minimum, right? But there is no maximum. If you look at this point, this is the minimum point. You see, all the function is above that, right? Absolute minimum. But if I look at the maximum power, my function is going above both ways, right? So there is no maximum. If I go far and look, there is a value going up and up and up and up. No max. And here there is no maximum, no minimum, because function is going to infinity, going to minus infinity, no maximum, minimum, both are not there. Here again you have a minimum at 2 points now, and you have a maximum here, right? So there is a maximum, there is a minimum. Minimum occurred at two different points, but it is the same value. You see, the value is equal. So absolute minimum is only one, but it occurs at two different points. This can happen. At two different points, you may have the same height or same bottom of the function. Here again, you don't have any maximum minima because it is going to infinity, it's going to infinity, right? And here you have a maximum minima because it is a closed interval. See, it means my function starts from here and it stops here. So this end point is my maximum, this end point is my minimum. So on a closed interval, maybe the end points are maximum minima, but on the open interval we are not sure what is happening, okay, and so on. So we have to consider different cases. For closed interval, I have a different answer. For so see, if you have a closed interval, he said if f is continuous on a finite closed interval, then f has both maximum and minimum. So on a closed interval, both maximum minimum will be there. Why is that? You see, if I consider closed interval f on closed interval AB when the endpoints are included, right? You know that closed interval is when all values of real numbers such that x is between a and b and the endpoints are included. You see, equal. X is greater than or equal to a, x is less than or equal to b. So this interval when a and b are included in your function. This is your closed interval, and function may behave something like that. So now you see, if your function from a to b is a straight line like that, then the endpoints become maxima and minima, right? This is the minima, this is the maxima, right? So, or if it comes down, like this, now this endpoint becomes the minima, this endpoint becomes the maxima, right? Because it is a closed interval. If you have a curve like that, even in a closed interval from a to b, if you have something like this, let's say, right, then see, this critical point becomes the maxima. Agree? So this is down, down, minima, maxima. Or you can have something like this, right? Let's say this is a closed interval. Again, my closed interval starts from a to b. Now you see, this critical point is maxima and this end point is a minima, right? So see, in all cases, my absolute maxima or absolute minima lie either on the critical point or at the end point. See, this is absolute maxima, this is absolute minima, right? Here, this is absolute maxima and this is absolute minima, right? So either at the end point or at the critical point. So all your absolute maxima minima occur either at end point or a critical point, right? So it means absolute extrema. Extrema means both maxima minima, right? Extrema occur at either a critical point, where critical points are the turning points, these top and bottom points, right? Or at the end point, or at end points of the interval, because it's a closed interval. So this is a very simple test for closed intervals, and it's always there. For a closed interval, you will never say that there is no maxima minima if f is continuous. So now what I will do, I will, in step 1, I will find critical points. Okay. What are the critical points? That is the points where f prime x is 0, right? Or corner points as well, or f prime does not exist, corner points. So does not exist means these type of corner points, right? Here f prime does not exist, and f prime 0 means where you have smooth turn like that, right? Here and here. So these are the critical points, and step 2 is I will just compare the values. Now you see, I don't have to find second derivative and see whether it is increasing, decreasing. No need to do that. Reason is, what I will do, you see here, if I compare these points, if I compare this highest point, this is the, let's say this is my critical point C1, this is my critical point C2, and this is my critical point C3, right? These are the critical points, these top point, bottom point, top point. Agree? These are the critical points where you have the turning points, right? So this is critical point, can be maximum minimum, but critical points are all these points. F of C1, F of C3, this is F of C2, right? And now you have end points. At the end, this is the end point. So this point is F of A. This is F of A, and this point is B. So if I find this point is F of B, right? So now I know that this is absolute maximum. This is the highest point, largest answer. right? And this FB is the lowest one here in this example, right? So it means I don't have to check whether my function is increasing, decreasing, whatever that is doing. What I can do, I can just evaluate my function, evaluate f at critical points C1, C2, C3, like I did here. I will evaluate this blue ones, and then I will uh, evaluate f at endpoints. That's it. I will just find the function value and compare which one is the largest. I will just do that and see which one is the highest and which one is the lowest. Highest gave me absolute maximum, right? And lowest gave me absolute minimum. Very simple test for closed interval. Then step 3, compare f values. Compare function values, okay? Largest or highest value will give me absolute maximum, and smallest value will give me absolute minimum. So no need to see in relative maxima minima. When we were here in relative maxima minima, we said what is happening to the left, whether it is increasing, then we see on the right whether it is decreasing. If it is from increasing to decreasing, we say that it is relative maxima, right? If it is from decreasing to increasing, it is relative minima. So we do a lot of things like that over there. But here in a closed interval, it's very easy to check the answer. So here it is written, the criteria, 3 steps. Okay. So let's see, this is my example, example 1 on page 268. 2x cube minus 15x square example 1, page 268. That was the page number. Yes. So 2x square minus 15x square plus 36. 2x cube minus 15x square plus 36. And the question is find the absolute maximum, absolute minimum values of the function on the interval 1 to 5. Well, that's it. Okay. So this is my function. What happened? So this is my function. So first of all, for maxima minima, I need f prime, first derivative, right? So first derivative gives me 2 into 3x square minus 15 into 2x plus 36 into 1. Agree? No issues? The derivative of x cube is 3x square is 2x, and x is 1. Right? So this becomes 6x square minus 30x plus 36. So now I will set it equal to 0, set f prime equal to 0. So if I do that, I will get 6x square minus 30x plus 36 equal to 0. So now if I take 6 as common, it becomes x square minus 5x plus 6 equal to 0. And from here I can make factors, x minus 2, x minus 3, right? 3 2s are 6 and 3 minus 2 is 5. So from here I got x equal to 2, and from here x equal to 3. My interval is this. So it means both are fine. Both are in this interval between 1 and 5. So I will accept both. If there is any point outside the interval, I will ignore it. Okay. So now I got the critical points. These are the critical points. Now step 2 was evaluate f. Now calculate f at critical points. What is f of 2? what is f of 3, right? And then we calculate at endpoints as well. So at critical points, my f is, so these are the critical points. So f, not f prime, f, this one, okay? This f, I have to evaluate the function value. So 2 into 2 cube minus 15 into 2 square plus 36 into 2, right? And then 2 into 3 cube minus 15 into 3 square plus 36 into 3. So these values are there, so I can just take it 28 and 27, right? So you can check it 28 and 27. But I have to evaluate my function at endpoints as well, right? You see, at the endpoints as well. So what are the endpoints? 1 and 5. You see, in this interval, endpoints are 1 and 5. My endpoints of the interval, because this is my interval from 1 to 5. So these are the endpoints. 2, 3. These are the critical points. So I have to evaluate my function at all these 4 points. So f of 1 is 2 into 1 cube minus 15 into 1 square plus 36 into 1, and f of 5 is 2 into 5 cube 15 into 5 square plus 36 into 5. So again these are calculated over there. So 23 and 55. 23, 55. So these are endpoints. So f at critical points, f at endpoints of the interval. Now which one is the highest? This is the highest one, right? So this is the largest and this is the smallest. So it is both came and the endpoints, but it's not always true. You see, your function may be like this. Endpoint is 23 and then 27, 28 and 55. Your function is like this. That's why the smallest value is at the first point, the highest value is at the end point. So these 2 and 3 are in the middle. They are not the highest and not the lowest. They are the critical points, but they did not give me the maximum. So checking is important. It may be like this, you see. It may be something like this, right? If this is the case, then you see the critical points become the highest and the lowest, not the end points. So that's why we have to check all of them. We cannot just say that end points are my maximum minimum values. So now I can say that hence f has absolute maximum value 55. 55 is the absolute maximum value, right? And that occurs at x is equal to 5, right? So I can say that occurs at x is equal to 5. And f has absolute minimum value. What is the absolute minimum value? 23, right? And that occurs at x is equal to 1. So at x is equal to 1, we have a maximum value, minimum value of 23, and maximum value is 55 that occurs at 5. So testing absolute maxima minima on a closed interval is very easy. Okay, this is the first test, right? So on a closed interval it is very easy. If it is not a closed interval or infinite interval, semi-infinite, infinite, open intervals, then it's not that easy. Okay, if it is, let's say the next one, they said semi-infinite or infinite, absolute extrema on infinite intervals. If the interval is infinite, right, so we do not know what is happening because endpoints are not there, right? So one of these things can happen, you see, because on both sides it's going somewhere. If on both sides it is going above, means if my limit goes to plus infinity, if I go to plus infinity, my function goes to plus infinity. If I go to minus infinity, my function goes to plus infinity. It means from both sides, it is going to plus infinity, no maximum value. But in the middle, you may have a minimum value, right? So you may have a minimum value. So relative minima, absolute. Absolute minima will be there. Okay, no maxima. You see, f has absolute minimum but no maximum. So no maxima, no absolute maxima, but there is a minima. So I can make this here. Second test was infinite intervals, not closed intervals, infinite intervals. Okay, if it is infinite intervals, then my function, like minus infinity to infinity, all interval is there, right? So my function may go something like this, right? But in both cases, if my limits are going to infinity, so if my limit goes to infinity, at plus infinity and at minus infinity, both limits are going to infinity, you see? So limit as x goes to plus infinity goes to plus infinity, and if I take the limit x goes to minus infinity, it also goes to plus infinity. So if your limits are both plus infinity, it means no maxima there, no absolute maxima there, right? But has absolute minima, and that will occur at critical point. You see, if it is something like that, coming down, going up, coming down, again going up, going down, going up, like that. So see, all these are critical points, 1 2 3 4 5, right? But see, this becomes the minima. This is the lowest point, this is the absolute minima. So one of the critical points will give me the minima. So what I will do, I will calculate the critical points and compare which is the smallest value, because this critical point is here, 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 and this one. So see, 1 2 3 4 and 5. So this is the smallest, right? This is the lowest value. So again, I will only compare the critical points. Okay, if you have something like this, if you have something like this, opposite to what we have. Now here you see, my function is going down on both sides. It means if I go to minus infinity or plus infinity, right, my both limits are negative infinity, plus infinity or minus infinity. Both limits are going to negative infinity. When you are going to negative infinity, it means my function is going to negative infinity, no minimum, right? So but I have a maximum somewhere like this one. So see, this point will become absolute maximum and no absolute minimum there, no absolute minimum, right? So this means that there is no absolute minimum, right? But f has absolute maximum at a critical point. At some critical point, it will have a maximum. So what I will do, I will compare critical points. The largest will give me the maximum. If my function goes down on one side and goes up on the other, then no maxima, no minima, right? So you see, if one limit, if on the left side goes down, right side goes up, right? Or on the left side it goes up and the right side it goes down, right? On the left side it goes to infinity and on the right side it goes to minus infinity. So one of them is plus infinity, one of them is minus infinity. So it means one of them is plus infinity, right? And the other one is negative infinity, right? So we are not concerned about where it is plus. One is up, one is down. So no maxima minima, right? So if one is plus infinity, no extrema, no absolute extrema there. Means both maxima minima are not there. Okay, so you can say that there is no absolute. Relative maxima minima can be there, but absolute are not there, right? So right, so 1 2 3 4. So see, no maxima minima, no maxima minima. Here only maxima, right? No minima. Only no maxima, only minima. Agree? So all these things are there. So whenever you have and same is the case for open intervals as well. Same is the case with open intervals. Anyway, let me do this example first. Or I can go to an exercise instead of that. These are the closed interval. So closed intervals are easy, right? We just find the critical points. Uh, Exercise set 7 to 16. So here I can write that. For open intervals, exercises from 7 to 16. These are for closed intervals. So you can pick one of them and solve. Okay. If I go to some exercise which is here, infinite intervals, you see, 21 to 28. Infinite interval or open interval. These two are open intervals as well. So open is the same like closed interval, infinite intervals. But let me do this one. 21 or 21 is, or 23 maybe. Let's do 23. 4x cube minus 3x4. Exercise 23. 4 fx is 4x cube minus 4x cube minus 3x4. Okay, and interval is plus infinity, minus infinity to plus infinity. So not a closed interval, right? Infinite interval. So all the exercises from 23 to 26, these are for the page 273. Page 273. So what I have to do first of all, I have to check the limits where my function is going on the left and on the right. Okay. So I will first of all look at the limits. Limits x goes to plus infinity of f of x. I have to check the limits first. And now if you recall the limits from chapter 1, when we take a limit at plus minus infinity of the polynomial, we just consider the highest order term. We ignore the lowest order terms. So what is the highest order term? Only 3x4. Okay, highest order term. So we just look at the highest order term. That's it. So that is minus infinity. And now I will check limit x goes to minus infinity f of x. That will be limit minus infinity. We can directly write highest order term here to save time, but I can write it now, minus 3x4, and x4 is always positive, so it is plus infinity multiplied by minus 3 is minus infinity. So see, both limits are minus infinity. It means that f has no absolute minima. Minima is not there because my function is going down on both sides. At plus infinity, it is going down, at minus infinity it is going down. Now in between it may have something, so I have to find the critical points now. In between I have a maxima at critical points. So there is a maxima at critical point. So to look for a maxima, we need critical point. To look for absolute maxima, we need critical points. So for that, I need f prime of x at 4x cube minus 3x4. So x4 has this derivative. 3x square, yes, correct. So now if I multiply, this is 12x square minus 12x cube. So if I take 12x square common, it is 1 minus x. So if I set this equal to 0, set f prime equal to 0, it will give me x equal to 0 from here and x equal to 1 from here. So these are the critical points. Okay, so now at these critical points, I will evaluate f at critical points. I need the values now only. So f at 0 is 4x cube, 0, 4 into 0 cube minus 3 into 0, 4. So that is 0. And f at 1 is 4 into 1 cube minus 3 into 1, 4. So that is 1. Okay, so it means this critical point gives me 0 is 0 and 1. So at 0 answer is 0, at 1 answer is 1. So it means my function goes like this. It goes to infinity and here it goes to infinity. So see, this 1 becomes the maxima, you see, right? So this 1 has become absolute maxima. So from here I can see the answer. So the largest is, so this implies that f has absolute maxima at x is equal to 1, right? And absolute maxima is also 1. Absolute maximum value 1 that occurs at 1, right? Both are the same. That occurs at x equal to 1. Don't say that 1 is the minima. Okay, this is the highest one, this is maxima. But 0 is not the minima. We have already told that there is no minima. So don't make this mistake, you see. We have already told that there is no minima. So see, 0 is in the middle. It does not become a maxima minima. Okay, so there is no minima and absolute maxima at 1. So that's how you can deal with infinite intervals. The same thing for open intervals. If you have open intervals a, b, where a and b are not included, a, b is all x values of real number such that x is between a and b. Equal is not included, means my a and b are not included. We only have the values inside, strictly inside, that's it. Okay, if a and b are not included, I cannot evaluate my function at ab, right? Because a, b are not included in my domain, right? So it means we cannot evaluate f at a and b. Not possible. So we do the same thing. So we follow same procedure as of minus infinity plus infinity, infinite intervals, as of infinite intervals. I will take the limit as x goes to a and x goes to b. Instead of minus and plus infinity, I will take the limit as x. So at a, we have the limit as x goes to a plus, because I can only approach a from the right. Okay, and at B I can only approach B from the left, so I will take the limit as x goes to B minus. If any one of them is plus infinity, there is no maxima. If any one of them is minus infinity, no minima. Right? So we will follow the same procedure that we did above. So for example here, exercise number 27 and 28, they are open intervals, you see, minus 5, minus 1. So let's try 27. Exercise 27. So exercises 27 and 28. These are exercise 27, 28. Okay, these exercises are for open intervals. So let's do 27. So 27 has fx is equal to x square plus 1 over x plus 1. And interval is from minus 5 to minus 1. Okay, so because it's 1 or minus 1? Minus 1, right? So I will take the limits for both. First of all, x goes to minus 5 plus. Plus means minus 5 is the left point, plus 1 is the right point, right? Minus 1. So I can only go to minus 5 from the right. And I can only go to plus 1 from the left. So from the left means x goes to minus 1 minus f of x. So if I go to minus 5, there is no problem because minus 5 is not in the denominator. So if I write x square plus 1 over x plus 1, I can just replace minus 5 here. So it will become 26 by minus 5, right? So it's a number not going to infinity. But here, if I take the limit at minus 1, it goes to infinity. X goes to minus 1, x square plus 1 over x minus 1, x plus 1. So see, if I put minus 1 here, it will become 0, right? So it is going to infinity. But I have to check whether plus infinity or minus infinity. This is a question mark, right? So I will see x square plus 1 is always positive, right? You see, x square plus 1 is always positive, right? That will remain plus. But here, if minus 1 minus means the values are on the left. We are here on the left. So on the left side, minus 2 will remain negative. You see here, when x is on the left, x is less than minus 1, then x plus 1 will be negative. You see, from here, x plus 1 will be negative. So we have plus at the top, minus at the bottom. So answer is minus infinity. Okay. So see, plus at the top, minus at the bottom. So plus divided by minus will give you minus. Agree? So if one limit becomes minus, it means there is no minima. So this implies that no absolute minima. Okay? But the answer equals to 0. Why 0? 0 in the denominator. If 0 in the denominator, above is 2. You see, minus 1 square plus 1 is 2. 2 by 0 is infinity. Right? 0 is in the denominator. So it is infinity. So now, no minimum is there. So I can look for maxima. And maxima occurs at critical points. Right? So now what is happening basically? At minus 5, my function is minus 26 by 5. Somewhere here. Okay, and at 1 it goes to minus infinity. At minus 1 it goes to minus infinity, going down. But here it is not going down, it's here at minus 26 by 5, by 4 or 5. 4. It is 4. 26 by 4. So minus 13 by 2, right? So this is your minus 13 by 2. So from here, it is giving you a constant number. Function is coming here. So in the middle, I may have a maximum now. So I have to find critical points. For maximum, to look for a maximum now, need critical points. So for that, we need f prime of x. F prime x, use the quotient rule. X plus 1 square, x plus 1 as it is, the derivative of the numerator is 2x, x square plus 1 as it is, the derivative of the denominator is 1. So I got 2x square plus 2x minus x square minus 1 divided by x plus 1 square. So this becomes x square plus 2x minus 1 over x plus 1 whole square. So if I set this equal to 0, set f prime equal to 0, so this will give me x square plus 2x minus 1 equal to 0. So are there any numbers here? So I can use quadratic formula, I think. So that becomes minus 2 plus minus 4 2s are 8. So it is minus 1 plus minus square root of 2. So minus 1 plus square root of 2 is outside. You see, minus 1 plus square root of 2 is outside. So we can neglect. This is outside the interval. Inside is only minus 1 minus square root of 2. This is my, so only critical point in minus 5 minus 1 in the interval is minus 1 minus square root of 2. Plus will go out. So this is the only point, right? So this will automatically give me a maxima. So I can just calculate my function value at this point and it will give me a maxima. So minus 1 minus square root of 2 square plus 1 over minus 1 plus minus square root of 2 plus 1. So you can calculate that this is our absolute maximum. Automatically only one critical point is there, it has to become a maxima. If there are more than one critical point, we will compare. But because we had just one, so that will automatically become a maxima. That's it. Okay. There is an easier test for both infinity and minus infinity. But that if we are lucky enough, the fourth and the last one. If we have only one critical point, no matter if it is open interval or infinite interval, only one critical point in minus infinity to infinity or in open interval AB, above two tests, right? Is it the third one? No, fourth one, yes. In above two tests for infinity, minus infinity and AB, if you have only one critical point, no need to check the limits. You see, in above 2 points, we were checking the limits, right? We first check the limits in these two intervals, right? So if you have only one critical point, no need to calculate limit as x goes to plus infinity minus infinity or limit x goes to a or b, a plus b minus, like that. Okay, why we don't need that? Because if you have only one critical point, then my function will go down and go back up, right? Or it will go up and come back down, right? Because there is no other critical point, it will not turn back up. If it turns back up, there is another critical point, right? And which is not there. Similarly, if it comes back down, you will have another critical point here, but that's not there. Agree? So if you have one critical point, it will only turn once. That's it. Then it will go up both sides, or it will go down both sides. So either you will have a minima there. So see, either you will have decrease on the left, increase on the right, or increase on the left, decrease on the right. But we do it in section 4.2. It means this is a relative maxima, right? But this relative maxima automatically becomes absolute maxima. And this relative minima automatically becomes absolute minimum. So if you have one critical point only, check whether it is relative maxima or absolute maxima. If it is relative minima, it becomes absolute minima. If it is relative maxima, it becomes absolute maxima. Okay, so it means if you have, if f has only critical point at x is equal to c, right, and f has relative maxima at x is equal to c, then f has absolute maxima at c. Automatically relative maxima becomes absolute maxima at c. And if f has relative minima at c, then f has absolute minima at c. Simple as that. So now we can go back and see how we can check relative maxima minima. There were two ways. Either we can check left and right, whether decrease to increase, increase to decrease, or we can also check that second derivative is positive at minima and second derivative is negative at maxima. We can check that as well, right? So if I look at the exercises here, sorry, let me finish. Right, so see, all in all these functions I think you have one critical point only. Let me check which questions have one critical point. The above question had one critical point. You see, the example which I did here has one critical point only. You see, x is equal to 0, not 0. This was the only critical point, right? So this can be done without using limits. So it means if I don't find limits before, if I don't find limits, if I check the critical points first, and there is only one critical point, I don't need to check the limits. I will just look at the second derivative, whether it's positive or negative, right? Hmm? No, if it is one critical points, then no need to check the limits. You can find the critical points first. If there are more than one critical points, then you cannot answer directly. Then you have to check the limits. Okay, but if there is only one critical point, no need to check the limits. Fine. All right, so let's see. I can pick some question. Maybe the first one, 29, x square minus 2x square. And the interval is minus infinity to plus infinity. Exercise 29 on page 273. He said use a graphing utility, means use a use some uh, program, right? But then he said use calculus method to do that. So I'm only doing calculus method. If you want to use graphics utility, you can do that. I can show you. There is a graphing calculator. You can write graphing calculator in Google, and Desmos is the website. If the net is there, this is also the problem in this room. We do not. That's bad. So now, uh, if it opens, I can show you that, but unfortunately, it's not coming up. Graphing calculator. No internet is coming. Anyway, no need. So I can first find the derivative. Let's hope there is only one derivative. 2x square minus 2x power 1, and then the derivative of inside is 2x minus 2. Right? So, no, there are more than one. So anyway, I can take 2 common from here. If I take 2 common from here, I will get x minus 1, and I can take x common from here. Let's say first I can take x common from here, and I will get x minus 2 inside, and 2 common from here, and I will get x minus 1. So it has more than one critical points. This is not the same example. I was looking for an example where I have only one critical point. So x minus 2, x square minus 2x, x minus 2, and x minus 1, 2x minus 2. Yes, there are two critical points. So it becomes 4x, x minus 2, x minus 1, 3 critical points. So here I will need limits. Right? So this is not the best example for that. Here also we have more than one critical points. More than one critical points. So they did not give me any question here with one critical point. Maybe this 28 also has one critical point. You see here, this has one critical point only. Anyway, if you have to complete this question, because critical points are more than one, if I set f prime equal to 0, right, I will get x equal to 0, I will get x is equal to 1, I will get x is equal to 2, right? So 3 critical points. So that's why I cannot use that method for one critical point method. I have to go back for this infinite intervals. So you know that at infinity intervals we need limits. If there is only one critical point, I will not find the limit. I will just check the second derivative. If that is positive, I will say that there is absolute minimum. If it is negative, I'll say absolute maximum. But if we have more than one critical points, now it means I need to check the limits as well. What is happening to plus infinity and what is happening to minus infinity. This is important now. So at plus infinity, my function is x square minus 2x square, right? So it will only give me positive infinity because it's a square, right? It's always positive. So both will give me positive because the whole square is there. So it is plus infinity. It means there is no absolute maxima. No absolute maxima. But for minima, I will calculate f. For absolute minima, I will calculate f at critical points. Right? I will evaluate f at critical points because one of the critical points will become the minima now. So if my minimum points were 0, 1 and 2. So f of 0 is 0 square minus 2 into 0 whole square, which is 0. F of 1 is 1 square minus 2 into 1 whole square. So that is also that is 1. And f of 2 is 2 square minus 2 into 2. It is also 0. Right? So see, 4 minus 4 is 0. So these two are smallest. Right? So this is largest. Right? And 0 is smallest. This is, there are two zeros now, so both are smallest. It means I got a minimum. I don't want a largest one because I'm looking for absolute minima. I don't want largest, I only want smallest because there is no maxima. So this is not the largest one. One is not largest because limits go to infinity. Okay, so maybe my function is like that. You add 0, it is 0, at 1 it is 1, at, so it is 1 here, at 0, so it is going like this, right? But after that it goes to infinity, after that it goes to infinity. So you see, we do not have this as maxima. It is a relative maxima but not absolute maxima, but these both becomes absolute minima. These are both absolute minima, and because they are going to infinity from both sides, so no absolute maxima. No absolute maxima, don't call it the maxima. It is a relative maxima. Okay, so it means that f has absolute minima of 0, and that occurs at 2 points. That occurs at x is equal to 0 and at x is equal to 2. So 0 is at 2 points, not just at 1. But minimum value is only 1. Minimum value is 0. That's the only one. But it occurs at 2 different places, right? So if you can open the calculator, you can see, I can show you the graph looks like what I made, right? Because I have some idea from these two we can enter the equation, it will show you the graph. Okay, and why the graph will be like that? Because I use the information that I collected. Function goes to plus infinity on both sides, and in the middle I have 3 critical points, and 2 are the smallest one and 1 is the one which is in the middle, not become the largest. So this does not become absolute maxima. But if this question is about relative maxima, you will get relative maxima here and 2 relative minimas. But these 2 relative minimas have become absolute minimas. Okay. I don't know why they don't have access in the rooms. Whenever we go to the rooms, there is no internet. If I stand at the door, there will be internet, right? They should not do that because they have this computer is gone. Sorry, a mobile you have. So something wrong with my laptop? Okay, so this is it in section 4.4. Next is section 4.5 that I will do next time. That is very important. Next is applications, applied maximum minimum problems. Basically, we will have real-time situations where we have to find maximum minimum of the function. And this is actually the real applied math. Okay, what we have done before just for our background, section 4.5, right? Very important section. So here some given problems will be there, and we have to find the maximum and minimum of some functions. So, So these are the real problems that we will do. They are also called optimization problems. You see, a garden is laid out in a rectangular area protected by a fence. What is the largest possible area if I only have 100 feet of wire available for fencing? So see, this is something practical. I want to make a rectangular area, but I want to fence it by some wire. And my wire is not infinity. Wire is only 100 feet. And I want to cover the maximum possible area with that 100 feet. So see, this is a problem of finding absolute maximum, right? But it's not a question like in 4.4. So these are very interesting examples. We will do inshallah next time. So, but before that, I should know 4.4. So I will suggest you to do some problems which I wrote here. That try these problems which I wrote here. Right. So look at these examples again and try to work with your questions. So today is, uh, so I